So welcome everyone to the evening session. Our first speaker is Oleg Brandt from University of Cambridge, and he will tell us about ANUBIS.
Excellent. Okay, so let's get started. Well, the story is obviously about ANUBIS, and ANUBIS is in fact somebody with a chacal head, and this is also what you can see in this picture. So this is ANUBIS at work, and I will leave it as a riddle for the time being, and I will tell you the solution to the riddle at the end of the talk. Okay, so first of all, where do we start from? Obviously, we're starting from the idea that we want to look for long-lived particles, and before really discussing the different experiments and how ANUBIS fits into this landscape, I just want to say to make a very basic kinematic argument. So there are essentially two different search strategies as I see it. There's one way to search for very weakly coupled light particles with high statistics. And then, of course, there's the option that these long-lived particles are quite massive or are produced from decays of heavy states, like, for instance, at the electroweak scale or maybe heavy mediators. And this is essentially the two different scenarios that I would like to consider. And then if you talk about the LHC or in general kinematics, and then this corresponds to two different measurement regions. So measurements from the first category, so for light particles, this is essentially along the beam axis of the LHC, and the measurements the search for heavy states is then orthogonal to the beam axis. So this would be essentially just a simple kinematical argument, right? So in the forward direction, you can produce a lot, and also with weak couplings. And if you want to probe something more massive, then you really want to cover as much solid angle as possible and likely look at transverse physics. Okay, so let's talk about along the beamline. One proposal that we also covered today is phasor, obviously. Now, ANUBIS is more from the other direction, so from the orthogonal direction, and this is where Codex P that was just covered in the previous session fits in, Methuselah as well. And what we proposed was essentially to instrument the service shaft of the Atlas experiment with a series of tracking stations. So these are those oval discs that you can see there, and that's essentially the idea of the experiment. The main benefit is, of course, to reuse the existing infrastructure, and this really is a big cost factor because civil engineering, as you know, is very, very expensive, especially at CERN. And the idea is really to use this main access shaft, which is 18 meters wide. And this gives you also nice acceptance. And also another aspect, which is quite important that I always make, is that the decay volume is projective, in the sense that if you look at this picture, the interaction point is somewhere there. So this tells you that the access shaft is almost projective, well, just a little bit, not perfectly projective towards the interaction point. So this is obviously good for acceptance. So you have this 56-meter long tube with 18 meters diameter that you could in principle use as a visual volume for your detector. So our current proposal is to take this shaft and to put 4 tracking stations into it with a total, with a cross-sectional area of 230 square meters per tracking station. So essentially you can think of it as round plates that will be put into this service shaft. And the next question is obviously, how do you do this, and how do you keep them in place? Well, first of all, you can belay them on steel ropes, and there is also a crane in that building which can carry up to 270 tons. So we are fine from that perspective. And once you have belayed on steel ropes your detector or your tracking stations into the shaft, you fix them to the sides with cams. So this is a cam that you know from mountaineering, and the principle is very similar. So you have feet that go to the side, and essentially it is the weight of the detector that stabilizes it. And once you pull the thing upwards, you can very easily extract it. So in case LHC or Atlas asks for access, then you can relatively easily extract those tracking stations. We don't foresee that this will be needed, but in any case, if you want to use the main access shaft of an experiment, you want to make sure that you're able to remove your experiment, your detector, on a time scale of a day or something like this, and not on a time scale of several weeks. Of course, this will not fly with Atlas, CERN, etc. Okay, so the idea is really to put into the shaft 4 tracking stations, and let me just tell you very briefly how the basic idea looks like. So this is a cross section of this shaft. So now this is looking from the side. So this is the shaft, and you're looking from that direction. And what I'm showing here is a tracking station 2 and tracking station 3, and each of them contain 2 tracking layers. So one triplet layer and another triplet layer, which are 1 meter apart. And this gives you a nice lever arm to do tracking and to do vertexing. So essentially, the idea is that you look at this fiducial volume, which is shown in orange, and you accept displaced vertices, which are reconstructed to come from within this fiducial volume. So this is an important point. You don't want to accept displaced vertices which are coming from the rock. You don't want to accept displaced vertices which are coming from maybe an upstream tracking station, because this may have just been maybe a neutron hitting another tracking station. So here on the right-hand side, I also have a basic table with detector specifications, and I will just very briefly go through them. If you have questions, you can ask at the end. So one very important one is timing. And this is relevant because you want to fiducialize your volume. So typically high energy collision particles, they're moving at the speed of light. So with if you want to fiducialize your volume and not to sacrifice too much of your fiducial volume, you can do this with timing requirements, right? So if you want to have a resolution of say 15 centimeters, this allows you to essentially use almost all of your fiducial volume. And this you can do with a timing resolution of only half a nanosecond. Then the next thing is obviously the efficiency. Well, I think that's fairly evident, so we'll not spend too much time talking about it. What's a bit more tricky is the angular and spatial resolution. So obviously you want to still be able to resolve different tracks. And you also want to be able to reconstruct the tracks, or to reconstruct the vertices from the tracks. So you actually need a fairly good resolution on the lever arm of your tracks. Now, if you take as a physics case K longs, I mean, you certainly cannot push lower than K longs. So this is the extreme case. And if you take physics, you make the assumption that physics is produced at the electroweak scale, so about 100 GeV, mass of the Higgs. You end up essentially with an angular resolution of 0.1 radian, which essentially gives you an idea about the spatial resolution. So this is important because this essentially defines how many channels you need, and the costs, the electronic costs, they often scale with the number of channels. So that's important. Okay, now coming to the detector technology. The idea is that each tracking station will be modular. So it's like a chessboard, and you have units, well, nominally 1 × 1 meter, but it can be also optimized for costs. Maybe it will be 2 × 1 meter. This is what we've been discussing most recently. And like I said, each of them is just, 2 layers, two triplet layers 1 meter apart, so that you can do tracking. And each of the layers is a triplet, so that you get a very high efficiency. And the secret is already betrayed here on the slide. So the idea is really to use RPC technology, so resistive plate chambers. And the reason for this is simply because it's cheap, and because they fulfill these requirements, right? So they have, at a reasonable cost, you can get very nice timing resolution and quite a high efficiency. So we looked into this a bit more in detail, and we found out that the BIS 7 and 8 prototypes that are currently being put into Atlas, they actually fulfill our requirements off the shelf. I mean, you can go to this company and you can have them produced. And they come with a timing resolution of 0.4 nanoseconds. And the costs also, well, they're not cheap, obviously, but it's reasonable. So we're talking about something like 5,000 Swiss francs per square meter. And this includes mechanics, gas caps, strips, etc., etc. The weight is also good, 30 tons, and that's much less than the crane can carry. And yeah, that's essentially it. Now, a couple of words about backgrounds, because this is also important. So how do we deal with the backgrounds? Well, typically, the backgrounds are long-lived particles from a standard model that are not electrically charged. So this is K-longs and neutrons, which have long lifetimes. Now we have the big advantage that we have Atlas as a passive shield, which accounts for about 10 nuclear interaction lengths. So this is the calorimetry mostly. But then again, 10 nuclear interaction length is not really that much. So the main idea here is really to use Atlas as an active veto. And active veto means that your neutral particles, they typically, like neutron K-longs, they normally come as part of an energetic jet. So you can use, you can make a requirement that your long-lived particle candidate should be sufficiently far away from any jet activity in your detector. And for this, you can use all possible handles. So you want to use jets reconstructed in the calorimeter, tracks, so jets made of tracks and reconstructed in the inner tracker, and also jets made of tracks in the neon spectrometer. Now you can already see from this that ANUBIS only works if it has if it lives in symbiosis with the main detector, with say Atlas or CMS. So the concept only works if ANUBIS is allowed to trigger the readout of Atlas. So if there's an interesting displaced vertex candidate, you read out the Atlas detector and you can check for the isolation and essentially how the event looks like. That's the main idea. Now, talking about Atlas, since this is important, this is how it looks like in the cavern on the left-hand side. So you have here a cross-section through Atlas along the beamline, and the lowest tracking station of ANUBIS is then above it in the shaft. And this is the region of the neon system that is covered by ANUBIS. So in principle, you have here the full coverage of the calorimetry, obviously, but then also you have very good instrumentation in the neon spectrometer. So you have 9 tracking layers and essentially 5 meters of an independent lever arm. Okay, enough about detector specifications. I think the rest of the talk should be really spent discussing the sensitivity, so the exciting physics you can do with it. And there we mostly focused on one specific benchmark scenario, which is, well, a Higgs decaying to a pair of scalars, which are long-lived, which then decay into a pair of standard model particles. You may ask, okay, why this particular benchmark model? Well, most of the conclusions, they're generic, but the main idea is really to have new physics produced at the electroweak scale. So this is why we chose a Higgs propagator. In principle, the conclusions should also hold for models like typical SUSY models with long-lived particles. You will be able to do that with that as well. Okay, and here essentially we are using as an input or as a benchmark to an Atlas search, which was using, which was also looking for this scenario for displaced vertices in the outermost region of Atlas, so in the neon spectrometer. And this is the main result plot from this paper. So this is the limit on the branching ratio, and you obviously want to push as far down as possible as a function of proper lifetime. So essentially you want to cover this region all the way to the Big Bang nucleus since it is bound. And that's precisely where the Atlas and CMS detectors are limited, just because the geometric acceptance at some point ends. So what we've done is we've simulated our signal with MATGraph, and we allowed or we required that the long-lived particles penetrate at least one tracking station. And then we considered two different background scenarios. So one of them is essentially requiring four or more signal events for evidence. So this is similar to Methuselah. So this is the optimistic scenario. And then we also consider a conservative scenario, which is saying 50 or more signal of events for evidence. And this is assuming a similar background to the muon spectrometer search that I just talked about. And we use these two numbers to bracket the sensitivity because for the Atlas only search, we should be able to do better than this because A, we fiducialize the volume, and B, because there is more active detector layers for the veto. So it should work even better. So anyway, the sensitivity is somewhere in this bracket, and this is why we give those two numbers. We also considered three different geometries, and one of them is the standard geometry, which you could also call conservative. So essentially, we require hits in two tracking stations. So a long-lived particle should go through two tracking stations, which essentially defines the fiducial volume to be this red region. Then there is also the one ring scenario, which is nice to know. And then the extended scenario is the one that you really want to deal with, that you want to consider, where the fiducial volume is essentially all of ANUBIS, or all of the shaft, and then everything in this cone from the interaction point towards ANUBIS. Okay, so this is these are the money plots. There are essentially two sets of plots, left and right, which are identical. And they show the different scenarios. So on the one side, on the left side, we have the one ring versus standard scenario. And essentially, this is the difference between, well, the lower line and the upper line of the same color. So two red lines, for instance. There are two sets of lines, a green one and a red one. And well, the green one is the conservative background scenario, and the red one is the optimistic background scenario. And the Atlas search is shown here in lilac on the top. So different mediator masses, obviously, but the main message is that if you compare the sensitivity of ANUBIS to that of Methuselah of Codex B, then you see that ANUBIS is playing in the same ballpark. And that's, I think, the main message that we want to convey here. Right. Okay, these are our findings, and this is the model that we looked at. But since then, also other groups have looked into other models, and I want to just give you a quick summary of this. I hope this is as complete as it gets, because I didn't collaborate with those people. These were independent studies. So one group, so Hirsch and Wang, they looked at heavy neutral leptons or sterile neutrinos, and well, this is Lagrangian. Essentially used a very similar detector setup as us, well, 14 TeV as us, and then they considered the optimistic scenario. And well, this is how it looks like. This is the sensitivity, and essentially they set limits on this guy, on the mixing with the active neutrino sector. And you can see that ANUBIS has a very similar sensitivity to the other proposals that are on the market. And the same is also true for the other models that they considered. So there's the left-right symmetric model and U1B left model, and also there the sensitivities they look good, they look reasonable. Another paper. Well, not another paper, but essentially the main bottom line here is in the abstract. I highlighted the relevant bits in red, and yeah, was very happy about it because this was actually my birthday present. I mean, this paper just came 2 days before my birthday in January. Okay, since then more papers have been published. So long-lived sterile neutrinos in effective field theory, that the exclusion contours of ANUBIS are competitive. I'm rushing here through this material a little bit in interest of time. And then similar study again on heavy neutral leptons with masses around the electroweak scale. And then again, there are two cases considered, Dirac and Majorana. So Dirac is in the left, Dirac is on the right side, Majorana is on the left side, and different effective field theory operators. There are more in the papers if you're interested, but essentially the message here is that ANUBIS, which is this dark blue line, has very competitive sensitivity compared to the other experiments. Okay, then if you believe in supersymmetry, obviously we also need to have a plot in supersymmetry. R priority violation and light neutrality at ANUBIS and MAP. Well, this is again shown as a function of lifetime, and here the limits. So you want to exclude as much of that as possible. So you want to push down, and you can see that ANUBIS is doing fairly well towards very long lifetimes, which is precisely what we want to cover. So we want to cover the thing that is very difficult to do at the LHC with the main detectors, so heavy masses and obviously very long lifetimes. Okay, let me summarize and conclude. So we get up to, so the projections indicate up to 3 orders of magnitude better sensitivity compared to current or approved future experiments for massive neutral long-lived particles with lifetimes of or decay length of 10 to the 2 to 10 to the 8. And this is true for particles produced at Lick-Trevik scale or more massive. Moderate costs. I mean, I gave you some idea about the costs, so that's very reasonable. And yeah, it has also a large and projective decay volume. So this is another big advantage, right? So you have this shaft, it's there, it's for free, you can just go there and use it. It's not quite as simple because obviously you also need to talk to Atlas at CERN or CMS and CERN, but the main point is that there are no civil engineering costs. And then, like I already mentioned, you can only operate ANUBIS successfully if it is used in connection with Atlas and CMS. So this may sound like a drawback, but in reality, it's a major advantage because with this, you can really get the full picture of the event, right? I mean, if ANUBIS says there is an interesting event, read out Atlas or CMS, then you know what else was produced in this event. And this is very interesting if you look at more complex models, for instance, gauge-mediated SUSY or split SUSY. Maybe there's, I don't know, a couple of energetic jets produced in the same event. Or maybe there's an ALP, which was produced in association with a Z boson, right? Then you can look for Z plus displaced vertex decays. So this is what's shown here in the sketch. So this is one of the main advantages of ANUBIS, that you have actually this feature to really get a better understanding of what's actually happening and get the full picture of the event. Okay, conclusions. ANUBIS stands for an underground belayed in-shaft search experiment. It's cost effective, can close the well, some of the sensitivity gap for proper lifetimes between 10 to the 2 and 10 to the 8 meters. Very cheap, not very cheap, but reasonably cheap because it eliminates the need for civil engineering. Physics reach comparable to Codex B and Methuselah. Again, there is this unique feature of being adjacent to Atlas and CMS and being able to see the full picture of the event. And I think I made this point already several times, but the idea is that ANUBIS is one-to-one transferable to CMS using its main PX56 shaft. And of course, it is also combinable with search strategies, right? If, say, Codex B is realized, then if there is still additional money and there is a physics case, then obviously one can also build ANUBIS, or if ANUBIS is built because it's cheap and then there are signs of new physics, then obviously one can still extend and build an additional detector. Okay, the next steps, just very quickly before concluding. Well, the first one, the obvious one, is ProANUBIS, which is a prototype. So this is essentially one piece of the tracking station. I was explaining you it's similar to a chessboard. So you just take one of those chessboard units. In this case, it would be 1.8 meters times 1.2 meters. So two BIS 78 RPCs, 1 meter apart. And the idea is to take such a unit and to position it within the shaft of ATLAS and really measure the fluxes of muons, neutrons, etc., inside the shaft in situ, and to correlate this with ATLAS. For instance, you can also use that in order to time in this detector with ATLAS, because you can take the muons which come from ATLAS. Yeah, there's a timestamp for that. And you can also check your timestamp in your prototype detector and essentially synchronize and correlate this one. So what needs to be done is a little bit of R&D for the next RPC generation, next generation of RPC detectors. So essentially checking optimize the pitch, because the costs scale with the pitch, fully integrate the readout electronics, because this saves the costs, and also ecogas, longevity, etc. I can tell you more about this if you're interested afterwards. Then another important point is to really do detailed simulations. So essentially using a Fugient 4 model of ATLAS, the cavern, the shaft, and correlate the results from these simulations with the measurements of the prototype. So really just to be 100% sure that there is, not an order of magnitude missing somewhere. Yeah, so there is obviously an exciting time and intense years ahead of us. Right, I promised you the solution of the riddle. So this is Anubis at work. Well, the Egyptian god Anubis, and if you remember, his role was to take the souls of the dead Egyptians and to bring them through the river of death to the other side, to the underworld, where they come back to life. So this is the parallel. So you have long-lived particles, which are produced at the LHC, which go to the other side, so to say, to this river of death, and then they emerge back to afterlife, they decay into standard model particles and displaced vertex. And that's essentially the idea behind Anubis as well. Okay, thank you.
Thank you very much for a nice talk. So time for questions. Please raise your hands or just unmute yourself directly.
Yes, maybe I have a question for Oleg. So which is the situation with ATLAS? So do you have discussions or going? Because you are linked really very, very deeply with ATLAS and or CMS.
Yes, yes. Yes. Yes, well, this is a very good point. In our case, yes. This is ATLAS. I mean, if you look at the names in front, yes, all these names are ATLAS, and for that reason, eventually we talk to ATLAS. Informally, it looks very promising. I mean, obviously, ATLAS is interested in this. Before we really start formalizing this, a couple of steps need to happen. I mean, what you probably want to see before committing to anything is really the results of this prototype and GN4 simulations. So essentially, GN4 simulations you want to do anyway, because you want to have the full model of the detector. And then obviously you want to correlate them with real measurements. So at this point, once this is in place, I think this would be the moment where one would really formally approach ATLAS and also the CERN Council, presumably, since it would be a new experiment, and go down this route. But up to there, well, informal discussions have obviously taken place, and we'll of course stay in touch.
Yeah. And if I can, and then I shut up, you know that you probably know that the PBC has restarted and we are setting up this physics center for FIFs. And I was wondering, since I didn't get from Claude Vallée still a name from Anubis, which is the situation there? Are you in contact with Claude? Do you ever,
yes,
because
yes.
We have already scheduled a meeting, but I didn't contact you because I didn't get any name yet.
Okay. Yeah, this was we discussed this in our last collaboration well, workshop, if you want to call it this
Yes.
way. And my understanding is that Martin Bauer, my collaborator, has been in touch with Jörg Jekyll. So maybe it's just a matter of one day.
Martin is in ANUBIS.
No, he's been in touch with
Jörg.
So,
okay, fine.
Yeah.
Okay.
So it's coming, this information.
It's coming, yes, because we have a meeting the 23rd and 24th of June already.
Mm-hmm.
So we should try to clarify before that. So if you can trigger the process a bit to try to speed up.
Yes, it's there. It's there. It's just perhaps not fully propagated.
Excellent.
Hi, Oleg. Thanks for the nice talk. I just had a tiny comment. Hi, good to see you. So it's exciting to see all this progress. I wanted to just make a small comment, which is that I think it's probably fair to say that all the external long-lived particle detectors, Codex, Methuselah, Anubis, except maybe for Phaser, make it an integral part of their strategy to interface tightly with their neighboring, big detector. So Codex will certainly be fully integrated into LHCb, if I'm not mistaken, and Methuselah will be integrated into CMS as a fully level 1 trigger system and so on. So, and again, I agree with you. This is not in any way disadvantaged. It's absolutely required to get the full physics picture. But I think it's sort of what we've realized is the thing that simply has to happen across the board. Otherwise, you're just leaving money on the table, right? Like as you know, otherwise you're not getting the full information. So it's definitely an important part of doing the physics right. Yeah.
Yeah. Well, thank you for bringing this up, David. I think for Codex B, we have to acknowledge that it will be you will not get the full picture of the event, right? So this is where Codex B has a little bit of a disadvantage, right? You can't get missing ET, etc.
Sorry. Yes, of course. But as much
because
as
LHCb
the detector gets,
is only a single arm spectrometer.
For sure,
right?
for sure.
So
I agree with that.
Yes,
absolutely.
For Methuselah, I think this is definitely the way to go. We were not sure whether this is something that is being actively pursued or not. I mean, this idea was mentioned, I think, in one of your first proposals. It's great to see that this is also the plan for Methuselah as well.
Yeah, I mean, I'll talk about this a little bit, but basically it's been part of the plan from day one, and we've gotten a few years ago, we started discussions with the CMS people, and given that given the upgrades, etc., it's kind of technically shouldn't be a problem. So indeed,
exactly,
it's the thing to do. Exactly. Okay.
Yes, so maybe let's
you're muted.
Yeah. So maybe let's move to the next talk.
Let me ask one question. At the qualitative level, what is the main advantage? I mean, with respect to study for this type of particles, just at Atlas, for example. Okay. I mean, you still have with Atlas, you have more or less 4 pi geometry. Okay. Here you have some geometric, small angle. Okay. Anyway, it's much smaller than 4 pi. Okay, 4 pi. Okay, you are close to the interaction point. Okay. Still the Atlas at the level of 10 meters detector. Okay. Where is it? I mean, where is the main gain factor? What is the size or background or at the qualitative level?
It's really it's several factors. So one of them is certainly the geometry, because even though Atlas is 10 meters in diameter, your vertex efficiency is really a very almost a step function as a function of radius. So it stops being efficient at around 6 meters, right? Mm-hmm. So if you talk about 6 meters, that's already not so much. Then another problem of Atlas, maybe also CMS, is that if you go in a forward direction, you get much more backgrounds, right? Yeah. So this is the challenge, right? So in principle, it's not really full pseudo rapidity, but in reality, it's perhaps more like 1.5 maybe 1.5. I mean, it's yeah. So that's one factor. The other factor is the fiducialization of your decay volume. Because if you are in a shaft which is filled with air, then obviously you still get decay longs, which you need to deal with somehow. But then the neutrons, they can only hit air molecules, which reduces this kind of background even more.
Mm-hmm.
For the Atlas Muon spectrometer search, if you look at where the displaced vertices originated, most of them come from the outer edge of the spectrometer, sorry, of the calorimetry.
Yeah.
So this is also why we give this bracket in terms of backgrounds. We say it should be, well, it's perhaps not as pink as for Methuselah, but it's well, it's probably better than what Atlas does, and this is why we give those two numbers.
So Dimitri, if I can add something, Dimitri, I mean,
yes.
your question's a good one, because in a sense, if you look at short lifetimes, none of these detectors do anything, right? So you need long lifetimes, okay? So if you have long lifetimes, then the efficiency really goes with solid angle times depth, yeah? So it's not even size, it's solid angle times depth,
Yes.
yeah? And if you think about it that way, the main detector has 4 pi divided by 2 or something, right? Whereas, ANUBIS, Methuselah have 4 pi divided by 10 or something, right? 10 or 20. So roughly speaking, geometrically, they are in fact the same, roughly. Like the external detectors have 1/10 the solid angle, but 10 times the depth, roughly. Yep. So in terms of geometrical chance of catching the long-lived particle decay, they are very similar. The problem is that when you have very long lifetimes, no matter what detector you're in, the decay is a rare process, which means you cannot afford any backgrounds. And in that case, for many long-lived particle modes, many searches actually, like Oleg said, have quite non-negligible backgrounds. And that's what you have to cut down by going external and using vetoes and having material shielding and all kinds of other things. So the backgrounds are, I would say, the 0th order issue. And the geometry is just the price you pay to get away from the collision and reduce the backgrounds.
Okay.
Yes, if I can add a comment, all these detectors, Codex, Methuselah, and ANUBIS, they need to have a very good control of the background, because they don't have any, if you want, particle ID,
energy momentum measurements.
Energy momentum,
right. Exactly.
So,
it's very crucial.
This is really crucial for them. So
Absolutely.
Because they have essentially sets of hits. This is what they have, nothing more. And timing.
Sets of hits. Yeah.
Sets of hits,
exactly.
And timing. So position and timing, of course.
Yeah.
But this makes the background issue really the issue.
Could not agree more. Yeah, could not agree more.
This is also, well, I would like to make this statement slightly more relative, right, to put into perspective. So there is a little bit of particle ID that you could do even with RPCs, right? So you can put pre-shower between the layers, for instance, and then you can do some basic photon ID perhaps or something like this. But you're right in the sense that you can't really
I agree with you,
momentum.
but now you're doing civil engineering. I agree with you, but now you're doing civil engineering by pouring 200 tons of material into the shaft. Ditto Methuselah, you're pouring 3 football fields of lead onto a layer. Like now you're doing some real civil engineering. You can build a submarine. So I agree with you, of course, but it's tough, right? It's tough to do calorimetry on this scale, even with just
not calorimetry. I'm saying some basic pre-shower, which is a steel plate.
But even that, like get a few radiation lengths per layer. That's a huge amount of tons of material.
Yeah, you think? No, I don't think it would be a big issue. I'm wondering if it is useful, because I don't think it would be dominated by photons in any case.
Oh, it's definitely useful, but what I'm saying is it would be incredibly heavy. Like if you actually want 1 or 2 radiation layers of iron per tracker layer, we've worked through this from Methuselah. And
agree with respect to the RPC for sure.
Yes. Yeah, and all the experimentalists are saying don't even talk to me. That's what they were saying. So maybe you guys can do it better because of the geometry or something. But for us, it's I wanted that as well, but I am not, at least for Methuselah, for example, I'm not optimistic. But maybe you guys can.
Yeah, but Methuselah is a soccer field.
Well, yeah, but I mean, I would say the consequences of dropping one are worse for
yes.
Oh yeah, really sure. No, but the crane.
Don't drop the plate.
Right. No, I mean the tracking. Each tracking station, just from not neglecting any pre-showers, is something like 50 tons, right? The crane can carry 270, right? So in principle, you have something like, well, let's say 100 tons that you could use per tracking station. It's not much. I agree with you, but that's something that we want to look into in more detail.
I think that would be awesome if that could be made to work. Yeah.
Okay, so now we can move to the next talk, I guess.